This video is designed to help you extend your knowledge of how to do some mixture problems. So we have one dry mixture problem here, which is ground beef and ground pork being mixed together, and we'll do a couple of liquid mixture ones with some acid and that kind of thing. So let's take a look at how this problem would work. If we look at it carefully, we realize that what we have is actually a knowledge that we have 8 kilograms of ground beef, as you can see from right here. So what we need is a variable for the ground pork. So we'll make P equals the kilograms of pork in mixture, and we'll make T the kilograms of total mixture. Okay, so that'll be beef and pork combined. Since we do know that there's 8 kilograms of ground beef. Now we can write an equation that keeps track of the total kilograms. So here's one for kilograms, and that's going to be the amount of ground pork plus the 8 kilograms of ground beef is going to give us T kilograms of total mixture. In other words, the total mixture, of course, is going to be 8 kilograms more than however much pork we put in. And now what we're going to do is try to keep a track of the dollars, the value of everything. So what we're looking at is, let's see, the ground beef is $4.75 per kilogram, but we know it's 8 kilograms. So when we do 4.75 times 8, what we're getting is the total value of all the ground beef in the mixture. Of course, we should add that to the total value of all the ground pork. And the ground pork we can get by doing $5.50 per kilogram times P, since we don't know how much pork is going to be put in there. And that should have the same value as the total value of the mixture, assuming that we're not trying to ring it up for a higher profit. If we're just trying to make them equivalent and say, well, to get our money back, we need to sell it for such and such an amount. Since we're going to try and sell it for $5.10 per kilogram, that's going to be 5.10 T. All right, so this gives us two equations with two variables, and what we're going to do is we're going to take this information right here and stick it in for T, and that's going to give us one equation in just P that we should be able to solve easily. So let's multiply some of this stuff out, and 4.75 times 8 is 38. So the total value of all the ground beef is $38 plus 5.5p equals 5.10 times p plus 8. Of course, now we need to use the distributive property, and that's going to give us 5.1 p plus, and if we distribute also here, so we're going to distribute to the p and we're going to distribute to the 8. So if we do that, 5.1 times 8 is going to give us 40.8, so $40.80 is going to be the total value, is going to be that value. So we've got 38 plus 5.5p equals 5.1 plus p, 5.1p plus $40.80. So let's see, subtracting 5.1p from each side is going to leave us with 0.4p on the left side. So that's going to be 0.4p. And subtracting 38 from each side, I don't really have room to write all of this, so just follow along. So subtracting 38 from both sides is going to give us $2.80. And so 0.4p is going to be $2.80. So we're going to divide each side by 0.4. So that's 2.8 divided by 0.4, and that's going to give us 7. So what it says is we should put 7 kilograms of ground pork in there. And if we do that, then we're going to have a total of 15 pounds of mixture. So you can go back and check for yourself that 7 kilograms at $5.50 per kilogram plus the $38 worth of ground beef should equal the same total amount of money as $5.10 times 15 kilograms, the average price that we're going to sell the mixture for. So just double checking that, we're going to get 5.1 times 15. So the right side is actually, and I'll just write this over here in the corner, $76.50. And the left side is going to be 5.5 times the 7 kilograms that we have, and that's $38.50 plus another 38, and that's going to be $76.50 as well. So over here we have 38 plus $38.50. So of course we have found the correct amount of pork to add. Let's move on to a couple liquid problems. So here's a problem, a solution problem, or a liquid mixture problem, as I like to refer to them. And you should be thinking about a 25% antibiotic solution as meaning that 25% of the volume in there is antibiotics. So that gives us a foothold to know how to keep track of antibiotics. And let's look at this problem carefully. It says, how many cubic centimeters of a 25% antibiotic solution should be added to 10 cubic centimeters of a 60% antibiotic solution in order to get a 30% antibiotic solution? In other words, we're going to dilute that concentrated 60% antibiotic solution and make it less concentrated. We're going to bring it down to 30% by adding an even lower concentrated antibiotic solution. So we should be able to say the amount that we're going to add. So let's call that A. A equals cc's to add of 25% solution. 25% solution. Sorry, the writing is so bad. I'm using a new pen here. It doesn't seem to be working very well. And let's make B, we already know what our we're gonna have 10% of the centimeters of the 60%. So what we don't have is the total. So let's make T equal total cc's of final mixture, final 30% solution. We'll just call it solution, SOL apostrophe N, or abbreviation N. All right, so we should be able to write two equations, one to keep track of the total cc's. So we're going to keep track of the total solution. So if we're keeping track of the solution, that's going to be the following equation. It's going to be A plus 10, that's originally in there, the 10 cubic cc's, the 10 cc's of 60% antibiotic, and that's going to equal T. So very similar to the structure of the previous problem that we just did with the dry mixture. Now, the way the solution problems work is 25% of however many cc's we put in is going to be how much antibiotics we put in. So to keep track of the antibiotics, and I'll just say AB for antibiotics, we're going to get 0.25 A plus, now how much antibiotics was in the original solution? Well, there was 10 cubic centimeters of a 60% solution. So 60% of that 10 cubic centimeters is antibiotics. So that means 0.6 times 10. And so that's going to give us how much antibiotic material was actually there. And that should be, since no antibiotic is either getting created or lost, it's just, we have it in our mixture, So the amount that's in there to begin with plus the amount we add should be the amount that's in there at the end in our total solution. So that's going to be 30%, so we'll make that 0.3 of some total amount of liquid, which we don't know yet. However, we can certainly substitute a plus 10 in for t, and that gives us one equation with one variable. So we're going to get 0.25a plus 6, which is 60% of 10, of course, equals 0.3 times a plus 10. And it's very nice that we have that 10 number because that makes doing the math really easy. So we have 0.25a plus 6 equals 0.3a plus 3, 30% of 10. And now we can collect our a's on the right side. Let's do that by subtracting 0.25a from each side. So let me actually write that in. Subtract 0.25a on each side, 0.25a, and be careful to subtract it from each side. And we'll subtract 3 from each side. So let me write that in green. So subtract 3 from each side, and that should give us an answer that means 3 equals 0.05a. So we're going to divide 3 by 0.05 because 0.30 minus 0.25 is 0.05. So we're going to do 3 divided by 0.05, and that's going to give us that A equals 60 cubic centimeters of the 25% antibiotic solution should be added. So there's the answer to that question, and you can check for yourself. We're going to then wind up with 70 total cc's, and 30% of 70 is 21, so we'd have 21 total cc's of antibiotics in there, and that means 25% of 60 is 15, and 15 plus 6 is 21, so this works. Okay, you should be able to check that for yourself by plugging back in to make sure that both equations are satisfied. Let's do one more problem. So here's a problem that on the face of it, seems a little bit more confusing, but if we just kind of keep to our guns and work the problem as we have been, we should be able to define variables, write equations, and come up with what we need. So we have 40 liters of a solution that's 50% acid, and we want to add some water to make a solution that's 15% acid. We don't know how much, so let's call that W. W equals liters of water to add, and of course we know that we already have 40 liters in there, but we don't know the total number. That total number, of course, is going to be 40 more than whatever W is. So T is total liters of solution in mix. Okay, so that gives us two equations. W plus 40 equals T, and we can write an equation that keeps track of the acid in the solutions. So that equation turns out to be kind of interesting because we have 50% a 50% solution to start with. So 50% of 40, so we're going to write 0.5 times 40 is how much acid there was to start with. And then we're going to add some water. So what percent acid is water? Well, it's 0%, so it's 0W, which you obviously don't really even need to write, but I'm going to underline that just to emphasize it. This is 0 times W, which means the water isn't contributing any acid. Still, you can write the equation just to kind of keep track of playing the movie in your head, that you start with a big bin of 40 liters of 50% acid, and then you're going to add some water. So add some water. But if you're keeping track of the acid, and let me write that that's what we're keeping track of here. We're keeping track of the acid. It's 50% of the original 40 liters plus however much acid we get when we add water, which is nothing. And that should equal the total amount of acid in the final solution. So that's going to be 15% of T. So once again, we can substitute. But wait a minute, let's put the brakes on. Do we need to? If you look at this, 0W is simply 0. So what we actually have is an equation that's already solved for, ready to solve for T, because there's only one variable in it. So this turns out to be actually easier once you set it up and you realize this. So instead of doing the substituting this time, you'd solve for W right away. But if we just solve for T right now, what we've got is half of 40, which is 20. So we've got 20. Not sure why that didn't write properly, so let me clean that up a little. You've got 20 equaling 0.15 T. So we're going to divide 20 by 0.15. How many times does that fit in? It's 133.3 repeating liters. So 133 1/3 liters is the total. And we started with 40 liters, which means if we subtract 40 from that, we're going to get 93.3 liters of water. So the amount of water that should be added is 93 1/3 liters. Now, we could have written an equation that kept track of the water instead of the acid, in which case the amount of water that got added was 100%, and you were half water to begin with because you were half acid. And at the end, you want it to be 85% water because 15% is acid, so 85% would be water. So if it makes you feel more comfortable, you could actually write an equation that keeps track of the water, and then you would need to substitute. However, this turns out to be a really nice way to do this problem, and you could go back and double check for yourself that 15% of 133 1/3 is going to give you the same as is going to give you 20 liters of acid, and you find that they add up together. The 40 and the 93 1/3 to 133.3. So this is actually, even though on the face of it it seems like a harder problem, it's actually an easier problem. And I hope that's been helpful in terms of clarifying how these liquid mixture problems work.